Hello everyone, I'm Xiao Yijin. Today we'll be learning about the basic principles and applications of ASON. So what is ASON? ASON stands for Automatically Switched Optical Network. Let's explain what it is with an example. These figures illustrate the intelligent navigation system that will be applied in smart vehicles in the future. This system collects real-time information about weather, accidents, traffic, and so on, and transmit the information to a data analysis system on the cloud. Based on the data analysis, the optimal path between the current location and the destination is automatically refreshed and selected. The ASON network system is the intelligent navigation system for the telecommunication network. When protection levels are configured, ASON can automatically switch routes to prevent service interruption when multiple fiber cuts occur. This figure shows the architecture of an ASON network. We can see that an intermediate control plane is added to the traditional network architecture, which enables automatic switchover control and automatic service protection and recovery by selecting network service routes using CCI. Before we can proceed further, we must understand a few concepts of ASON. The first concept is TE. TE is the traffic management link. ASON NEs can exchange and compute traffic data through TE links, as shown in the figure. TE links of optical layer ASON are carried over optical layer overheads, and TE links of electrical layer ASON are carried over electrical layer overheads. The second concept is control link. Control links implement automatic discovery and maintenance of OSPF links between two NEs using the OSPF protocol. In this manner, OSPF control link information is spread over the entire network. Each NE obtains their desired information and performs the corresponding operations. The third concept is shared risk link group. As shown in the figure, when fiber cuts or other faults occur on an optical fiber due to external factors, the other optical fibers in the same optical cable may be under the same risks as well. These optical fibers can be configured as an SRLG during route optical fiber configuration. Now that we understand TEs, control links, and SRLGs, let's have a look at the 5 SLA levels provided by ASON based on different service requirements. As shown in the figure, the SLA offers increasingly stronger service protection from level 5 to level 1. Level 5 offers no protection. Level 4 offers rerouting and resistance to multiple fiber cuts. Level 3 offers 1+1 protection, which can resist multiple fiber cuts. The fault recovery time for the first fiber cut is less than 50 milliseconds. Level 2 offers rerouting 1+1 protection, which can resist multiple fiber cuts. The fault recovery time for the first fiber cut is less than 50 milliseconds, and the fault recovery time varies for subsequent fiber cuts. Level 1 offers the strongest protection, diamond permanent 1+1 protection, which can resist multiple fiber cuts, and has the shortest fault recovery time. Now let's have an in-depth look at the 5 SLA levels. Level 1 offers diamond permanent 1+1 protection. As shown in the figure, when either the working path or the protection path is unavailable, the rerouting function will lock a new lower-level protection path. This way, the service can be restored within 50 milliseconds for the first and subsequent faults. When resources are available, Level 1 offers resistance to multiple fiber cuts and high-quality multiple-level protection. The resource change is visualized on the NMS, and the reliability is 99.999%, making it suitable for the protection of high-demand services such as voice and VIP. Level 2 offers diamond rerouting 1+1 protection. As shown in the figure, when both the working and protection paths are unavailable, the rerouting function will lock in a new protection path for service recovery. This ensures that the fault recovery time is less than 50 milliseconds for the first fault, but varies for subsequent faults. Because the follow-up protection does not have pre-locked protection paths. When resources are available, Level 2 offers resistance to multiple fiber cuts for multiple level protection. Level 3 offers Diamond 1+1 protection. As shown in the figure, it offers only one-off protection, which is 1+1 protection. This means that when a fault occurs, it can be recovered only once, with service recovery time of less than 50 milliseconds. Resources are visualized on the NMS. Level 4 offers Silver rerouting protection. As shown in the figure, when a fault occurs, the service will try to reroute until the service is recovered. This level of protection can also resist multiple fiber cuts. When limited resources are available, Level 4 offers resistance to multiple fiber cuts and multiple level protection, but the fault recovery time varies. Level 5 offers no protection and is also called Copper services. Once a fault occurs, the services will be interrupted without rerouting. ASON supports multiple routing policies on the NMS. ASON also supports service path optimization, preset rerouting, and rerouting reversion. Services can switch back to the original path after a service fault is fixed. Now let's look at actual network models to figure out how service protection and recovery are implemented. Here are two models. The model on the left has two Silver services. For Silver Service A, the service path will be rerouted to that of Silver Service B when a fault occurs. When another fault occurs on Silver Service B, the service paths of both Silver Services A and B will be rerouted to the idle path in the middle. Similarly, the model on the right has a Silver Service B. It can resist multiple fiber cuts, and its services can still be restored by rerouting after multiple fiber cuts have occurred. The protection mechanism is individually deployed for each service with restricted protection and recovery time to ensure that more services can be successfully recovered after multiple fiber cuts. ASON also provides various recovery strategies, such as shared resources for the working and protection paths, additional service routing paths, and intermediate regeneration boards that can change wavelengths to avoid wavelength conflicts. When there is no regeneration board, wavelength conflicts can be resolved using adjustable wavelengths. This provides stronger service recovery capabilities. After the protection and recovery mechanism of ASON networks, we can now have a look at the types of ASON networks. There are two main types of ASON networks: optical layer ASON and electrical layer ASON. In application, the optical layer ASON focuses only on the interconnection between FIUs and the OTUs, while the electrical layer ASON focuses on the OTUK logical ports on tributary boards and line boards. So what is the technical difference between optical layer ASON and electrical layer ASON? Optical layer ASON implements wavelength protection using optical layer ROADM. It is applicable only to small or medium-sized short-distance transmission scenarios due to optical layer restrictions. The electrical layer ASON implements ODUK sub-wavelength protection based on electrical layer cross-connections. Without optical layer restrictions, it is applicable to large-scale long-distance transmission scenarios. ASON networks provide huge benefits to carriers, which are mainly reflected in the following aspects. For example, it can accelerate network evolution and provide customers with multiple SLAs with different experiences. It is more reliable and offers resistance to multiple fiber cuts with a network availability of 99.9999%. And it offers carrier simplified network O&M, reduced OPEX, automatic protection and recovery, flexible expansion, and greatly reduces O&M time. Up to the fourth quarter of 2015, Huawei has more than 250 optical layer and electrical layer ASON networks, serving 50 global carriers. The earliest ASON network has been in commercial use for more than 8 years.